Hello and welcome back. Let's take a look at a couple more questions where we apply vector addition and subtraction. So in this case, we have ABCD, which is a parallelogram. In this parallelogram, we are told that BD and AC are the diagonals and they intersect at a point E. We have to prove the statement EA plus EB plus EC plus ED equals 0. They're all vectors. So I'm going to start off by writing out the statement I must prove. So this is EA plus EB plus EC plus ED equals 0. Now recall that in a parallelogram, the diagonals bisect each other. And to bisect means to divide into two equal parts. This means that AE equals EC. And also, BE equals ED. Now, since vectors EA and EC, so EA and EC, lie on the same diagonal, and they're directed in opposite directions, and the vector magnitudes are equal, then we can express one in terms of the other. So I will leave EA as is, and I will express EC as the opposite of EA. Similar to this, we'll say that vectors EB and ED, since they lie on the same diagonal, are of the same magnitude and opposite direction. So they're opposite vectors. So I will leave vector EB as is, and then I would express vector ED in terms of EB. So it is the opposite of EB. So now let's take another look at our statement. It has changed face, obviously, no value. And notice how here we have vectors EA plus negative EA, so that would add to 0. In this case, I will simply rewrite the statement and bring the opposite vectors next to each other. Plus EB minus EB. And that is only for the purpose of explaining things. And obviously we can simply write the statement from this step here. Okay, so that would be equal to 0. So 0 equals 0, which means that we have just proved what we wanted to. Now let's take a look at our next example. Now this example is in the textbook, so it's one of your homework questions most possibly. And I selected this question so that we can practice it together. So M is the midpoint of a line segment PQ. R is the midpoint of TS. Now, whenever we read problems, especially in geometry, it is very important that we follow along with the diagram so that we can make the connection between what we're given and what we're trying to find, a visual connection. So, M is the midpoint of PQ. M is right here. This is PQ. So that means that M divides PQ into two equal line segments. R is the midpoint of TS. Here is R. Here is TS, so TR must equal RS. We're also told that PM and MQ are equal, and they're both A. Let's take a look at PM and MQ. So here's PM, here's MQ, and the diagram indicates in here that both vectors are given the name A. TR and RS are equal to B, so here is TR and here is RS. These are two equal vectors. Now we have to prove that 2RM equals TP plus SQ. Again, I will write the statement first. And then I will try to transform either each side or one side of the statement and make it look like the other. So you can do either or, but remember we cannot take terms from one side to the other when we're making or when we're solving proof problems or when we're proving statements. So I'm going to start off with TP, and I will try to express TP in terms of the other vectors in this diagram. So for TP we have, I'm going to bring this a bit closer here, further down, so we have the room. So for TP we have right here TR plus RM plus MP. Now I want you to focus or to observe something very interesting. So remember that this is the right side, by the way. So remember that here is vector TP, which we express in terms of these other vectors. So notice the first letter in the sum of the vectors and the last letter in the sum. So starts with T, ends with P. And this is not a coincidence, right? So that's supposed to happen, especially when we deal with vectors in closed polygons. Similar to this, we will express the vector SQ, here is SQ, as the sum of SR, RM, MQ. So now let's take another look at our expression and see what we can replace with what. Now TR, so TR is vector B. RM is simply RM, and we have no problem keeping RM in the expression because remember that at the end, after we simplify this, we need to obtain an expression that contains an RM. Now the next term is MP. So vector MP is the opposite of vector A. So we'll write plus negative A. Vector SR, here is SR, is the opposite of vector B. RM, so RM can stay in the expression. And MQ, which is vector A. So see the convenience of notice the convenience of using a lowercase letter to describe a vector. So it's easier to see that these two vectors, for example, are opposite than seeing that, well, TR and SR are opposite. So this is a more obvious resemblance of vectors. So now we are simplifying. So you see that we have vector B and negative B. So two opposite vectors which will add to 0. And we also have vectors negative A and positive A which add to 0. So we are left with two vectors RM. So or 2RM. So the right side has simplified to become 2RM. So which equals the left side. So with this we have proved the statement as required. So this was the end of lesson U1A2 part 1 when we added and subtracted vectors. And thank you for watching.